happens to me every day. Thank you. So this essentially the experiment proved that okay, they used a beam of electron and made to fall on a material target. I can say crystal, but they were not aware that it was a crystal. It was due to the accident that it became a crystal, and then the electron was made to fall on a crystal, and then when so it was already known when a wave when a wave interacts with a crystal, there happens something diffraction, and that follows a particular law or particular condition, which is known as Bragg's condition. N lambda is equal to 2d sine theta. And assuming that electron also behaves like a wave and also falls on a crystal with a defined lattice distance d, then people thought, okay, it should also follow the same condition. N lambda is equal to 2d sine theta. Through that, they calculated the lambda. They got one value, 0.165 nanometer. And then de Broglie, on the other hand, gave this relation that lambda can be equal to h by p, that where p is equal to before it was for waves electromagnetic radiation. Now it is a p momentum with a mass of a particle m, and then velocity, and then we also have the relativistic factor there. So I think we covered all this, and then we essentially from that lambda which we got 0.166 nanometer, we essentially proved that okay, particles can also behave like wave under certain conditions. So this is where we finished our yesterday's class. So today we will talk about the uncertainty principle. So before going to the uncertainty principle, I would recommend you to so I'll finish off the uncertainty principle, and not only for uncertainty principle and for the upcoming class. So in the next class, if I finish the uncertainty principle today, maybe I'll just brief you about the upcoming class. We will focus on Schrodinger equation. I'll give you a short introduction that why such equation was needed at that time, and why is the very foundation of the quantum mechanics. So far, if you have noticed that I was repeatedly saying quantum theory was proved, quantum theory was successful, the Planck's idea was successful. Einstein used the theory and he proved that photoelectric effect, etc., etc. And then Compton also used. De Broglie's idea was also based on the quantum theory. So far I was using the word quantum theory, but then it's to distinguish that from the quantum mechanics itself. Quantum mechanics is also based on the quantum theory, but then that has a separate foundation which was laid by Schrodinger later on. But before going to that part, we will cover what is uncertainty principle. So it is a principle. So it's again a fundamental. It's a fundamental law. It is inevitable in nature. But what I wanted to tell you all is that if you're all using, I just hope that you're all using author Beiser book. So if you go to the author Beiser book, not now, after the class, so I would like to go through by yourself, because if I go to those areas, then it will be beyond the scope of the syllabus. So if you later after this class, if you can like just read just give a read and try to understand this certain topics, like in the chapter, it's chapter 3.2. So chapter 3.2, 3.3, and then 3.4. So essentially, maybe I'll just give you extremely brief. And essentially, chapter 3.2 talks about waves, and 3.3 talks about describing wave, and then 3.4 talks about phase and group velocity. So why I am why am I highlighting these things is that so these are very necessary in order for us to understand the mathematical representation of the wave. Okay, so we're just trying to understand whether the electromagnetic radiation behaves like a wave or a particle. So far you just you must have came across this wave particle wave particle duality, so many things. But then how do we describe a wave? And so we can understand when we talk about the wave, the first thing comes to our mind is water waves. So the water wave is nothing but the displacement of the water itself with respect to the position. So the water surface is displaced in a wavy format. That's one sort of a wave that we can imagine. The other sort of waves are the sound waves. It's the compression and expansion of the pressure in the air, which creates sound. So these are the waves which were well understood, and we can have an visual image of those things. But when we are going into this level, when we are going into the quantum realm, or when we are going into the atomic scale, it may not be those sort of mathematical descriptions may not be equivalent or may not be satisfactory to describe the waves of this scale and of this behavior. So it's necessary for us to understand the wave through a mathematical perspective. So this 3.2, 3.3, 3.4 will give you an introduction about how a wave can be described through mathematics. So what kind of functions that it can what kind of functions that can describe a wave in a successful manner in order to for us to use it for application, so on. So just an extreme foundation of the wave, like representing a wave itself. So just that you can later on you can go through it, and then if you have any doubts, we can discuss about that in the next class. So you can raise those questions. Irrespective of that, now we'll go to the uncertainty principle itself. So let's see. Let's so which one more thing I wanted to, before going as a prerequisite, is before going into this concept. See, when in reality, it will never be a single wave. So the single wave definition is for us to simplify the formulation. But in nature, the light or the electron comes as a group. They comes as a wave packet. So they come as a wave group. So when we talk about wave group, it's always a superposition of multiple different waves, which would eventually give us a wave group. So it's like a superposition of different types of waves would lead us to a wave function or a wave like this. So it will have a final wave, something different. I hope you kind of get what I'm trying to say. But let's imagine a wave of this sort. If you see in the middle of this wave, the amplitude is maximum. Let's imagine, and then let's try to analyze this wave. This is a wave. So if you want to measure the wavelength of this wave, so you start from one peak, and then you finish it off with one single wave, and then you will measure the wavelength of the wave itself. That's one thing. The another thing is, since we are talking about the wave property as well as the particle property, how can we define where the particle would be in this wave at a given time t? So then it comes out that since the particle can be spread out throughout the way with respect to time, then we are restricted ourselves to talk in terms of probability. So we say the probability of finding particles towards the extreme of these waves are lesser than the probability of finding the particle in the middle of the wave. So then from now on, we will be handling the position not in terms of precise location, because when you talk about when you just say if you have a ball inside a room, You can say, if somebody asks you where is the ball in that room, you can just point it out, the ball is there. But that's not, if that, let's say that's not satisfactory to that person. So in every room will have a corner where you have, this sort of structure. So it will have an x-axis. We can define at x-axis, y-axis, z-axis, and depending upon the where the ball is, if you make this as an origin, you can always tell them with three different coordinates. So the ball is in x1, y1, z1, and which means the ball at rest is at it has a defined position. So you can define its position with a very high level of accuracy. But when we are dealing in the macro world, when we are dealing with the the observable world, these things are pretty much possible. But when we are going into this wave particle duality, when we are again going into this quantum realm, it's very difficult to say that the particle would be here at the same at the given time, because then the whole concept of the wave itself is lost. If the particle is here all the time, then there is no wave at all. So when there is a wave, that the particle's nature is spread out in the space, representing a wave. And from the observing this particular wave, we can say there is a high probability at a given time you might find this particle here more than here. So then we are talking about the probabilistic nature of the particle's position. This is one thing you should be aware of before talking about the uncertainty principle itself. Now let's go to let's try to analyze the uncertainty. Is it clear so far what I'm trying to say?
Yes, sir.
Yeah. So the only point I wanted to be aware of, maybe it may not be completely understood, but at least you just assume that this is how it works in the wave world, or the quantum world, if I may say. So we will always be from now on we will be talking about the probability. For a different kind of wave, the probability of finding the particle's position will be different. So when we talk about position, your first thing you should come to your mind is it's either zero. It's not going to be either zero or one in terms of probability. It can be any point, and that this probability distribution defines with the wave function. So these things again and again I will repeat during the Schrodinger equation. Then it would make more sense. But then these are all very abstract. I'm giving you. I'm trying to give you an caution. From now on, what we are going to deal is going to be extremely abstract. So it might be very difficult to grab the concept of it. But irrespective of that, I'll try to give time to time an real world application or analogy, so that it might make more sense to you. But before that, you must have noticed that there would be a theory and people would do an experiment to prove it, or there would be an experiment and people will come up with a theory to explain it. So this was the nature of the sessions that we had so far. But from now on, we will be talking about more abstract mathematical formulation of the quantum mechanics itself. So then we'll again go to the uncertainty principle. So we all know, even from the lab experiments which we did, so a measurement will always have some sort of an uncertainty. Even if you go to any level of precision, you will have an uncertainty. You will have a standard deviation. You must have seen so far in the science that whenever you measure a quantity, the quantity will be like x plus or minus delta x, where delta x being the uncertainty measured for the x itself. So let's keep having that in mind. Let's go to that. Let's see what happens. Let's say we are trying to measure the let's say we're going trying to measure the position of this particular wave, uh, um, and then let's define the uncertainty in the position as delta x. You can say the particle, the probability of finding the particle is very narrow within the space, which in turn will which with that logic we can say that the uncertainty in the x is also very small. I hope it makes sense that you can easily say that the particle is somewhere in between this wave, So the uncertainty of the position is relatively small compared to the uncertainty of lambda. So for this particular wave taken into consideration, it would be extremely it will be extremely difficult to measure a single wavelength because the wave itself is smaller than a single wave, so it will be difficult to measure the wavelength. So in order, because of that, you have a huge uncertainty in terms of measuring the wavelength, and we all know there is a relationship between wavelength and the momentum. So when you have uncertainty in measuring the wavelength, then you will also have the uncertainty in measuring the momentum. So for a wave of this kind, when the position can be measured of a wave of this kind, then the uncertainty of the x is low, but the uncertainty of the momentum, the same way where I say the delta x as uncertainty in the position, we can say from the wavelength I just explained, we can say the uncertainty of the momentum is very high. Okay, it's very low. So this is scenario number one. Let's talk about scenario number two, where you have a defined wave of this sort, let's say. So you have enough wave to describe your lambda. Therefore, your uncertainty in measuring the momentum might will go low, but you have a huge space, and then since it's a probabilistic nature, and also it will be very difficult to point out where the particle will be at a given time. Then, for that reason, your uncertainty of the x should go high. So this is the basic limit. This is a limitation in our system when we go into the quantum world, and this whole principle is known as uncertainty principle. So basically, we can summarize this what I've tried to explain now, as it is impossible to know both exact position and the momentum at a given same time. So this is the fundamental limitation. So this principle was proposed in the year of 1927 by Werner Heisenberg, and it's one of the fundamental physical laws of nature. So now let's also try to analyze this more rigorous in terms of mathematics. So as I told you that a wave of this sort might be like can be a superposition of 1 plus 2 plus I'm not drawing the wave because it's not so nice. So can be a superposition of 1, 2, 3, or more than an n number of waves could reproduce a wave. So that we can when we are trying to define it, so it's nothing but, if let's say we are trying to define a wave with a wave function psi of x, can be equal to the integral of 0 to infinity g of k, and then the whole wave group can be described with let's just imagine that it can be described with a cos function. So this integral 0 to infinity is the number of waves that we are going to add, just a representation. It's the number of waves that we are going to sum together to produce one single wave, which is phi of x. So this particular function can describe any wave or any number of superimposed wave. And then let's analyze this function itself. So we can say that the first component of this function contributes to the amplitude of the wave, and the second component describe the wave component, like describes the wave function, describe the shape of the wave itself. So this contributes to the amplitude of the wave, this contributes to the shape. In a very abstract way, I can say like this. So now I will try to draw four different scenarios, and then you can see what I'm trying to say. So let's say you can define the wave function position through xn, the wave function itself, and then so this is your position space, and similarly for a position space you will have a momentum space, which corresponds to the amplitude of the wave function. So I'm trying to draw a different scenario for this mathematical equation in terms of position space as well as momentum space. So you might wonder what is K. I'm sorry, I forgot to tell you the relationship between the K and the lambda itself. K is in also in a mathematical terms, K is defined as the wave number. So we know lambda is it's nothing but a wavelength. So it's a measurement in the unit of length. K is nothing but K is equal to 2 pi lambda. So the same lambda can be measured in terms of unit of radians per meter. So 2 pi radians per meter. So representing the same, again going to the concept of representing the same system into different coordinates. So now we are trying to represent this into a circular or polar coordinates. When we do that, we introduce this term called K, and the relationship between K and lambda is given by 2 pi by lambda. So now you would understand why this I call it as the momentum space. Now, whenever I talk about lambda, whenever I talk about K, it's directly related to the momentum of the system. So that's why I say that this is the momentum space and this is the position space. So now we also know the relationship between the lambda and K. So K is known as wave number. So if you just want to know more about it, you can search for wave number. So you will get an idea what is a wave number is. Uh, Irrespective of that, we'll go back to this formulation. As I told you, let's see for a different scenario how our momentum space will be, and then so this form of integral is known as Fourier integral, and when we do so this is another mathematical concept. A Fourier integral is where it's a summation of many different function to if the Fourier integral is nothing but a summation of n number of functions together can be said in terms of Fourier integral. But if the Fourier integral can undergo a certain transformation called Fourier transform, so which would eventually give the amplitude function of the wave of the curve. So again, I'll try to explain. It might be a little difficult, but you will understand towards the end. Let's say if our position function is well defined with a single peak, the Fourier transform just in terms of mathematical, the Fourier transform of this particular Fourier transform of this particular peak would look something like this. So when our psi of x, so position is well defined, the Fourier function transform of this function, which relates the amplitude and the wave number, would have this sort of tendency. The same way when we have our position function slightly spread out, then we will have our amplitude function, which is corresponds to the momentum space, to be in a narrow, will have a narrow peak. After doing this Fourier transform formulation, will have this narrow peak. But when you actually have a position function of this sort, a pure wave without any distortion in terms of amplitude to a particular space, will have the momentum space of this kind. Will have just one single peak. And it's also here I have to introduce that a term called Gaussian function. Again, these things can be slightly tricky, but then we'll just try to take it in abstract form. Fourier transform of a Gaussian function will in turn will give you a Fourier will be also a Gaussian function. Gaussian function sometimes is also represent or like can also be called as a bell curve. Fourier transform of a bell curve will be the bell curve. So why am I talking about all these things? So you can clearly see through mathematics that when a group of wave can be described of this sort, with an amplitude component and with the group of wave component. So like 0 to infinity means this has the n is equal to 1 comma 2 comma 3 comma dot dot dot. So many number of waves superimposed can be described using this one single function. When we analyze this single function, let's say if our function has a position peak like this, then we will have a broad momentum space. So you can clearly see when the position is well defined, it's very difficult to define the momentum. So we have a very broad curve. But when the position is spread out, so you can see when the position is small, the momentum, describing the momentum becomes difficult and it will have a broad function. But when the position is spread out, the momentum will in turn, description of the momentum will in turn reduce. This is the point is, now I'm not talking about any experiment, now I'm not talking about any physical relation. This is just a mathematical outcome of analyzing a wave. But since it is related to the wave number of the mathematics of the function which we defined, that's the reason I'm connecting it to the momentum of the system. Since it's related to the wave number, you can find, so this is this again I tell you, this is the position space, this is the momentum space. So this is this when the position is less spread out, our momentum mathematically looks like it's more spread out. Also confirming that what we have seen previously, that our this is how our uncertainty in the position and the momentum can be defined, and this mathematical approach also proves that. But what is the reason of talking about this is this to find what is the least standard deviation in terms of uncertainty that we can have, so the least standard deviation of this whole function can have for the Gaussian functions. And this is related as the delta x, which is the uncertainty in the position, and delta k, which is the uncertainty in the wave number for this mathematical relation as of now, says for the Gaussian function should be equal to half. So this is the least standard deviation you can get for the functions of this sort. So, but it's not our waves are not going to be in similar to Gaussian functions all the time. So it is safe for us to say that the product of the two uncertainty will always be greater than or equal to half. So this is where we end up. Know that from the wave number definition, we can say that k is equal to 2 pi by lambda, and we also know that lambda is nothing but that is a relationship between lambda and momentum. So the k can be related to the momentum by 2 pi p by h. So with this we can define p is equal to hk by 2 pi. So we have our p, and so let's then the uncertainty in momentum should be equal to the uncertainty in the k by 2. So we also know that delta x times delta k is h by 2 pi. So eventually this relation would have something of this sort. So delta x delta p should be greater than or h by 4 pi. Having this 1 over 2 in mind, this would be our final relationship, and this is known as the this is the same uncertainty principle in a mathematical representation, that when our delta x is going high, then when our uncertainty in momentum, uncertainty in position increases, then the uncertainty in the momentum should decrease to match this condition. Or vice versa, when the uncertainty in the momentum increases, the uncertainty in the position should decrease in order to satisfy this condition. So the same uncertainty we have explained in terms of mathematical relation. So here I can maybe read it out. So this equation states a product of uncertainty delta x in the position of an object at an instant, and the uncertainty in the delta p in the momentum component, is same at the same instant is equal or greater than h by 4 pi. See, so at this again, I will go back talking about the like physical interpretation of this. So these uncertainties are not due to the inadequate of the apparatus, but due to the imprecise character in the nature of the quantities involved. See, it's not because when we are dealing our lab, I was saying that there are multiple reasons, there are multiple sources of error. So there are multiple cautions that we have to take care in order to get the proper measurements. And we also know, let's say we are handling with a vernier scale, and if the edge of the vernier scale is somewhat broken or somewhat damaged, that would cause some uncertainty in our measurement. But this is not the uncertainty due to the measurement itself. This is the uncertainty due to the fundamental nature of the quantum world. Fundamental nature when we are dealing with quantum world. That's what we can finish off this explaining the uncertainty through the mathematical terms. Is there any doubt at this point?
No, sir.
If anyone else, if you have at any point, if you have any doubt, please you can interrupt me at any time and try to ask me. This mathematical approach maybe feel like little rigorous, but try to take the message away. So that's what we are trying to do. But the next part, what we will see is that the same uncertainty uh, can also be expressed in a different terms, and that would be more straightforward. So this is kind of telling us that we are limited in terms of defining the nature itself because of its wave particle duality. See, you can understand the the fundamental difficulty of this whole arise from the fact that our on a quantum scale, on a quantum level, the entire nature behaves completely different. When we are talking about you might have understood defining a position of a ball inside a room. It's very simple, it's very straightforward, it will be extremely accurate. Nobody will have a question. No, we will not have any problems of this such. But when we are going into the quantum realm, when we are going into this quantum world, this wave particle duality and all these if I may say, crazy principles brings these sort of uncertainties. But the same uncertainty principle can also looked or viewed through an observer point of view. Let me try to explain. Maybe that would make sense. So imagine that we have a probe, uh, uh, and then we can use that probe to now it's a thought experiment. So these experiment may not be really possible in the real world, but let's just assume there's certain condition. So imagine that we are using a probe, and then we are trying to take a photograph, or we are trying to see, when I say see, through our eyes we are trying to see an electron. Okay, so this is our objective as of now. So when you might already know, in order to do a measurement we need to touch them. So just to give an analogy in the physical world, so in order to do a measurement we need to do some sort of manipulation in order to take the information, in order to take the data out of it. So to measure the length, we bring the scale nearby, and then we measure them. And then likewise, I can give so many different examples that this is how the measurement is done. Again, coming back here, so in order to see the photon, we need to use some sort of light. So let's say we are using a light of wavelength lambda. So our probe instrument will emit a wavelength of light, will emit a light of wavelength lambda, so that we can see the electron itself. See, this is where the problem. So let's say the electron is let's just imagine that the electron is under rest, and we are using a light of lambda. We are using a light with a wavelength of lambda, which would have a momentum, because we know that the lambda and the momentum is related like this. So which clearly says that We know from all the experimental fact, again, the uncertainty in the lambda can be expressed in terms of h over lambda. So with this, you can clearly say from all the experiments which we have seen so far, in order to see the electron itself, we need to probe them and we need to touch them. So when this whole light interacts with the electron, it's inevitable that we will transfer some of the momentum from the light itself to the electron. It's already stating that it may not be possible for us to estimate the momentum of the electron itself in its previous state, because we are already disturbing the system with the light of lambda, with the light of a defined wavelength, which would have a momentum, and that there would be some sort of momentum transfer happen. There is a straightaway implication that we are having some uncertainty in the momentum, and that uncertainty in the momentum is related to the lambda like this. So let's say if you are using, if you are using lambda of, if let's say if you are using lower lambda, which means low wavelength light, your momentum, your uncertainty in the momentum will drastically improve. But if you use if you use larger wavelength, then you can achieve lower uncertainty in the momentum. I think it's very clear. Let's say if you use if you use lower wavelength of light, there will be a lot, it will have huge momentum, and then which in turn will give more uncertainty in measuring the momentum of the electron itself, because there will be huge transfer in momentum to the electron. But if you use larger wavelength, okay, then you can reduce the uncertainty in the momentum. So basically, in order to get the best uncertainty in the momentum, our proposal is that we are going to use a very large wavelength in order to see the electron. But then the problem not stops there. We should also know the position of the electron, and then you can see we can see that because light is a wave phenomenon as well as the particle phenomenon, we cannot expect to determine the electron's location perfect accurately regardless of the instrument used. So the reasonable estimate of minimum uncertainty of the measurement of one photon, so, is that I will try to explain that part now. So now we have understood what is the uncertainty in the momentum itself. So we have an electron. In order to see the electron, we should use some kind of a probe. Let's say we use the electromagnetic radiation of light with a defined lambda. But then the lambda is related with the momentum like this, and then when those two interacts, there will be a momentum transfer, and then we will have the measured momentum will have some sort of uncertainty. So, but in order to reduce this uncertainty based on this relation, if to an experimentalist, we can suggest, okay, you have to use a lambda of you have to use a larger lambda in order to have less uncertainty in the momentum. Then he will try to perform his experiment. But then if that person also has to measure the position, see, this is what the problem is. If we use a very large, because the position, if we use, it's intuitively straightforward. If you use a very large wavelength, which might, so if you use very large wavelength, so this might go past through the electron, which makes it extremely difficult to see the electron itself. So in order to, so larger the wavelength, larger the area it would spread out, and when we are larger the space that it would spread out, then it will very difficult to say that whether the electron is here or whether the electron is here or whether the electron is here. Then how to reduce this problem? We have to reduce the wavelength. Let's say we use of a wavelength of this length, then we can clearly say, okay, the electron is here. So for in order to estimate the position exactly, we have inevitably pushed to a place where we have to use a low wavelength. Again, I repeat, in order to estimate the position from this relation, you must have understood, if you use a very large wavelength, then it might be very difficult to exactly point out, okay, this is where the electron is. Sorry, any questions?
No, sir.
Think somebody. Can everybody mute yourself? Sorry. Okay. Yes, coming back to this point. So I think I finished the momentum side, and then I'm trying to explain how we can estimate the position itself. So when we use of a wavelength of a large size, it might be difficult to say where the electron is, because I just explained large wavelength means large, it will cover the large space, and then it will be difficult to define where the electron is, which intuitively we can say then, oh, okay, then use the smaller wavelength, then you can say where the position is. So then we can say that the uncertainty in the position is directly related to the lambda. So you can see the momentum is inversely related, and the uncertainty of the position is directly related to the lambda. If you use lower lambda, you can say the position in a very precise manner. If you use larger lambda, then your uncertainty in the position should increase. So this is the uncertainty in the position, and this is the uncertainty uh, in the sorry, this is the uncertainty in the position, this is the uncertainty in the momentum itself. So you can already see the contradiction. In order to get the best momentum, we need to use larger wavelength. So we will get best uncertainty in terms of momentum. But when we use the larger wavelength, our information about the position is lost, because we are using larger. In turn, in order to estimate the best position or best uncertainty in terms of position, we have to use small wavelength, which in turn will incur huge variation in the momentum or uncertainty in the momentum. So again, we can say that the product of these two should be somewhat greater than or equal to h. So this is a crude representation. This is not this is more true in terms of observing, or in terms of estimating the uncertainty itself. But this crude approach should also leads to the same result, that the uncertainty of these two, position and momentum, will always be greater than or equal to the lowest unit of in terms of quanta, which is h. But it might be in an experimental point of view, it might be more it might be easy to understand this particular concept, the same uncertainty through this concept. Okay, so with this, what's the time now? 9:50. Okay, with this we can conclude this class. Please, if you have any questions or any discussions, we can have. So, but this is the whole principle of uncertainty itself. So, any questions, any discussions? So I might have missed something, or I might have rushed through certain points. If you ask questions, I can come back and revisit and maybe give you a better explanation. Yeah, several plane wave packet. Yeah, exactly. So this is what I was trying to explain. Any no questions? Very hard to say that you don't have any questions in uncertainty, because it's not a straightforward thing to understand. Can feel free to unmute and talk, or share your comments based on this. What is your level of understanding in this? Should I repeat something? Should I give an overview? So I pasted the attendance link in the chat box. You can give your attendance. Meanwhile, if you have any questions, please talk to me. I hope some of you or most of you would have got the overall idea what I'm trying to say. But then with this we conclude the uncertainty principle. So please have a reading of chapter 3.2, 3.3, 3.4 before coming to the next class, which is tomorrow. And tomorrow we will talk about the Schrodinger equation. Again, I'm giving you an heads up that it's going to be very abstract. It's very difficult for us to construct a reasonable framework in our mind talking about these things. But I'll try to give as much of analogy as I can at every different stages, in order to in order to make you understand in a better way. Any doubts? Okay, after tomorrow's class, I will give you a set of sample problems, just sample exercise problems you can work out when in your free time. They'll be very, very simple, but then I'll first give you a set of questions. It's not a test, it's for a practice. So you can work out those answers, and later on I will upload the solutions as well in the next class. Is that okay?
Yes, sir.
Yes,
Yes, sir.
At least I get
so
response for
you
this.
haven't given the solutions for the questions you gave us previously.
Was it? Okay. Okay, I might have forgot. Sir, is there any lab manual? Yes, there are lab manual, but for the first experiment, I'm not giving you because I'm not conducting any quiz. But ideally, the structure proposed was so basically, I'll try to the first experiment. Basically, from the video, you can write everything, the apparatus, and I also gave the template. Right, from what you have observed, you can write those things. From the next class, I will give you lab manual, will be more helpful. And since it's being more helpful, I will also introduce quiz in the lab the session. And that quiz will correspond to 3 marks. Yes. And that quiz will correspond to 3 marks. And you will also get as a help as a lab. Arshita, I want to say something? Oh, this problem. Okay. I will upload or I will share.
Thank you, sir.
Okay. Yeah, so if you have all given the attendance and if you don't have any questions, you can leave now. Thank you. So those who have questions or any discussions, you can stay back. We can discuss for a while and then we'll end the class.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
You.
Thank you, sir.
Thank you. Thank you.